Welcome back. So let's take a look at the situation where we have a mass falling here. So we have an object here that I'm just going to let go and let it fall. As we think about the force diagram, because we can never escape that, the forces acting on this as it falls is we have the force due to gravity, specifically weight. It is a conservative force. It is the one on our list so far. Because it is a conservative force, I know that the work conservative is equal to the negative change in potential energy from the work energy relationships. So the force, work is going to be force times displacement. It is falling, and so the force is the weight acting down. The potential or the change displacement is going from here to here. It is in the same direction as the force, so they are going in the same direction. So from a vector point of view, let's make it easy and consider down to be positive. If we consider down to be negative, it doesn't change anything, then they'll both be negative. But as it's falling, it is a positive value. Well, HI is bigger than HF, and so the distance it travels is HI minus HF, and that's equal to the negative change in potential energy. And actually, we can expand on that. Change is always U final minus U initial. If we can substitute mg in here and then distribute, so I have mg hi minus mg hf is equal to, distribute the minus sign, I have ui minus uf. So I have this formula here. So the question is, what equation can I use for the potential energy that will work here? Now, I have some initial value minus a final value here. I have initial value minus final value here. It would make sense that if U is equal to mgh, that this works. Now, there are an infinite number of formulas that actually satisfy this because, well, actually pause it and see if you can figure out what is another equation that would also work to satisfy this. And I'm going to take a breath here, step back, let you think. Now, I'm assuming that you've paused it, you've started it up again, and you know what the answer is, but just in case, on the odd chance that you've gotten distracted and you missed what else it could be, we can always add any number to it. So if the formula for potential energy is, say, mgh plus 5, well, if I plug in that into here, so I'd have mgh initial plus 5 minus mgh final plus 5, the 5's are going to cancel out, and what I'm left with again is just mgh initial minus mgh final. So we can always tack on a constant over here. Now, when we get to more sophisticated physics, it's called a scalar potential, but that we don't need to know that. But we can always add a constant. What this means is I can establish 0 where the potential energy is 0 anywhere I want. So if this is, say, 12 meters and this is 3 meters, I can figure out how fast it's going when it gets to the 3 meter mark easily enough. So when the force we're dealing with is weight, or if little g is relatively constant, we can use mgh. So I'm now going to erase this, and we'll just do a quick little problem here exploiting this idea. And so now, I know that the the work non-conservative is equal to the change in energy. This is one of the work energy relationships. There are no non-conservative forces, and therefore there is no non-conservative work. So this would be equal to force non-conservative times the displacement is equal to E final minus E initial. This is 0 because the only force acting on it is weight, and that is conservative. And so we end up with 0 is equal to E final minus E initial, or E initial equals E final. In other words, energy is conserved. Let's take it down that next step. This is equal to my initial kinetic plus my initial potential is equal to my final kinetic plus my final potential. What's the formula for kinetic energy? I'm assuming that you said it correctly. This is 1/2 mv initial squared. And over here will be 1/2 mv final squared. My initial potential energy, what's the formula for potential energy? I'm hoping you said which one. The one associated with a relatively constant force due to gravity, in other words, a relatively constant weight. That would be mgh initial plus mgh final. And so at this point, we tried to figure out what can we get rid of. And so since I can establish 0 to be, for potential energy, the height is equal to 0 anywhere I want, I'm going to establish it here. It doesn't matter if we establish the other one, and we'll work through that after we do this one. So I'm going to let h is equal to be 0 here, and therefore my initial height, since this is 0 and not the ground, my initial height is going to be 9 meters. If that's 0, that's got to be 9 meters because there's a 9-meter difference between the two. And so my h final is 0 because I say so. Now, my initial velocity is 0 because that's given in the problem. So that's 0 because the initial velocity is 0 meters per second. And so my formula has now been reduced to a very simple mgh initial equals 1/2 mv final squared. Mass cancels out because it's a common factor. And so v final is going to be equal to, that's the final speed, it's going to be equal to the square root of 2gh initial. And you might want to convince yourself of that. I've seen some very strange math things on tests and stuff like that. So you might want to make sure that you can convince yourself that this is true. And so assuming this takes place on Earth, this becomes 2 times 9.8 meters per second squared times my initial height of 9 meters is equal to v final. And so v final becomes, and let me grab a calculator from over here. To enter 9.8 times 9 times square root. And I get a final speed of 13.28 meters per second. And yes, again, that is the final speed. It's not the final velocity because energy, these are not vectors here. These are scalars. So 13.28 meters per second. That's how fast it when it gets to this point right here. Assuming that you have written this down, or at least paused it and written it down. Pause it now if you want, if you need to, because I'm about to erase. I'm now going to establish a different h is equal to 0 here. So instead of that, I'm going to choose h is equal to 0 up here. And so now what is the height here? Now when you're dealing with vectors, you decide the positive and negative direction. But with here, you don't have that luxury here because we're dealing with scalars. So as you head towards, in the direction of the gravitational force, since we're dealing with gravitational potential energy, it becomes negative. And so the height here is -9. And that becomes critical because otherwise you'd end up with the square root of a negative, and that the math people frown upon that. So all of this stays the same, none of that has changed. This is mgh final, and do better markers than that. So what changes here, initial speed is still 0, and here, I probably should get rid of those vector symbols there. And here, this is 0 because I said so. I established h is equal to 0 up there. And so our equation now becomes zero is equal to 1/2 mv final squared plus mgh final. Mass cancels out because if I divide everything by the mass, that goes away. And then I end up with 1/2 v final squared is equal to -gh final. Don't worry about that minus sign because it's going to cancel out with that one. And so VF is equal to the square root of negative 2GH final, which is the square root of negative 2 times 9.8 times negative 9. And you end up with the exact same thing, whatever that number was, 13.28 meters per second. If we ended up with a negative under the radical in the end, something has gone amiss if it's physically possible, and it should be physically possible. If I drop an object, it should actually have some speed. All right, I think we are now ready for the ski slope problem, so I'm going to stop this and draw up the drawing.